Hello. In this sequence we will continue our tour of OCaml with the construction of some basic expressions. The rule of expressions is to compute values. In OCaml we have a very rich system of values, and in fact values play a very important role in OCaml. For this reason, expressions too play a very central role in the definition of the language. A first construction which is very important is the construction of a conditional expression, which is always written if condition, then first expression, else second expression. Here it is important to note that this construction always gives you an expression and not something which could be called an instruction.
An expression always has to have a type,
which means that, of course, the condition has to be of Boolean type, and furthermore, the two expressions that you have in the then and in the else part have to be of the same type, and this type will give you the type of the complete conditional expression. There is in fact a default value which is used in case you don't write an else part, but please don't use this for the moment, as this default is not what you might expect it to be.
Here we have some simple conditional expressions. The first example would be a typical use case. We have, of course, always in the conditional part an expression which must be of Boolean type, which is the case here. And then we have two expressions in the then part and in the else part, which must both be of the same type. Like in this case, the condition, of course, would be evaluated to true, which means that the result of this evaluation would be the result of the then part, which is, of course, 13. An important thing to remember about conditional expressions is that the types of the expressions in the then part and in the else part must be the same, otherwise how could we obtain a type for the complete conditional expression? As we can see here in this example, it is not the case, and in fact the OCaml system tells us that we have committed a type error. However, we are of course allowed to combine conditional expressions with any other constructions that we might know about expressions and obtain something nested and more complicated, like it is the case in this example. Here we have a conditional expression which is combined using conjunction with another Boolean expression, and this is of course perfectly okay and gives us the Boolean value true. Finally, another kind of nesting that is perfectly allowed in Boolean conditional expressions. Here we have a nested expression as the condition, and this is of course okay, and what we obtain in this case is, as expected, the value true.
We may also construct expressions by function application. In order to know how to use a function in constructing an expression, you have to know first the type of your function. In general, the function may expect several arguments, and in this case the type is written as the sequence of all the argument types and the result type at the end. All of these are separated by arrows. To apply a function with several arguments, you just write the name of the function followed by the different expressions which calculate the values of the arguments. For example, you might have a function like string.get, which expects first a string, then an integer, and which returns a character, and you would apply this function just by writing down string.get, then the string, and finally the integer.
And this would give you, in this case, the letter C, since strings are indexed starting from 0.
As you can see, again, parentheses are a priori not needed. They would only be needed in case you have more complicated expressions in which you have to indicate structure.
The examples on this slide demonstrate how we can apply a function which expects several arguments, like in this case the function string.get, which expects first a string argument and then an integer argument, and we just write down the name of the function followed by the first argument and then the second argument, and we obtain of course the result as expected, which is C, the third character in this string. In fact, you are allowed to write at the position of the actual argument any expression which computes a value of the expected type. Like for instance the second and the first argument might be more complex expressions which are to be evaluated before passing the values to the function, so we could also have something more complicated like this function application, which gives us, in this case, the character L, or as in the following case, we have a different kind of computation where we first convert an integer to a string for the first argument and a string to an integer to obtain the second argument.
Expressions, in fact, may be arbitrarily nested and may become very complex and complicated. You may, in this case, use local definitions in order to cut a large expression into smaller pieces, as we will see, in fact, next sequence. Functions may a priori be undersupplied with arguments. If you try to do this, then you get in general a result of a different type than you might expect, as we will see in week 4. Again, parentheses are a priori not part of function application. If you try to write something like f parentheses e1 e2 parentheses for a function application of a function with 2 arguments, you will get an error, and the explication for this will be given in week 2. Operators are just functions with a particular syntax which allows you to write down an application in an infix notation. Operators, since they are functions, always also have a type, like for instance plus has type int, arrow int, since it's the usual integer addition. We have already seen some operators which have in fact polymorphic type, like the comparison operators, since these operators may expect values of any type. In this case, the type of the arguments is indicated with the so-called type variable. Type variables are indicated by an initial quote. In case these variables consist of only one letter and a quote, they are in fact spelled like Greek letters. So in our example, we would have alpha, arrow alpha gives bool. Type variables can be instantiated, but since they are type variables, of course, they can be instantiated only by types. And as you can see on the example alpha, arrow bool, this means that the variable, of course, has always to be instantiated by the same type in one application.
So this is just to recall some things about polymorphic operators, which we have already explained in a previous sequence. A polymorphic comparison operator expects always 2 arguments of the same type. So if we try to apply it to 2 values of different types, we obtain a typing error. However, if we have several invocations of a comparison operator, then we are of course allowed to compare values of different types and the different invocations, like in the following example, where first we compare 2 integer values, then we compare 2 floating point values, and finally we compare 2 character values. We can of course combine the results obtained by Boolean operations, and this is perfectly okay, and we obtain the Boolean value too.
One final word of warning: the comparison operator is for us always written with a single equality sign. In fact, there exists in OCaml an operator written with a double equality sign. However, it means something else, as we will see in week 2. As always, you can find much more information in the OCaml manual, and if you want to learn about the complete set of constructions for expressions, you can find it in the reference manual of the OCaml language in the chapter on expressions.